speakers, Principal Dr. Hari Vasudevan, Vice Principal Dr. Shekhokar, Head of Department Dr. Amit Deshmukh, my dear colleagues and fellow participants. Let the illumination of the lamp in the virtual room mark the auspicious beginning of this FDP. So let's have the lighting of the lamp, Vivek. Yeah.
Kurutvang kalyanam arogyam dhanasampadam Shubham kurutvang kalyanam arogyam dhanasampadam Shatru buddhi vinashaya Deepajyotir namostute Deepajyotir namostute Shubham kurutvang kalyanam arogyam dhanasampadam Shubham kurutvang kalyanam arogyam dhanasampadam Shubham kurutvang
To carry things forward, Victor Hugo said, "Nothing is more powerful than an idea whose time has come." Today, AI is dominating the conversation. Since its inception more than 100 years ago, there isn't a Nobel Prize in computer science, and yet Geoffrey Hinton is its most recent recipient. For the uninitiated, he's the guy who found the method, backpropagation, that enables neural networks to learn, which is one of the two keys that unlocked machine learning and triggered the current maniac rise of AI. The point to note here is that backpropagation is a blatant take on medieval branch of signal processing, adaptive signal processing. All the buzzwords, pattern recognition, estimation, detection theory, are traditional signal processing topics which have merged into the AI field. Coming back to Hinton, 2018, he won the Turing Award, the computer science equivalent of the Nobel, for his work on convolutional neural networks. Once again, CNN is essentially repeatedly applying filters to extract patterns from images. We've been doing that since image processing was conceived. Convolutions are multiplications in the Fourier domain. Guys, let's put it up front. It's not the signal process engineers moving into ML. It is the CS guys trying to use signal processing. The general incumbent is that AI is completely a CS thing, and EEs coming in this field are due to lack of job opportunities. Points to ponder. The ROC characteristic comes from estimation theory, which was established for detection of objects using radio signals. Reinforcement learning uses a lot of Markov chains. Caramel filters also part of Gaussian processes. It's not machine learning in signal processing, but signal processing in machine learning. Dear participants from all over the country, we will spend these weeknights talking about and debating, irrespective of where AI came from and where it would go. Would Ray Kurzweil be proved right when he says AI will pass the Turing test? Will the point of singularity be nearer? He has put a date, machines surpassing humans, through in 2029. Let the patent be passed on to the 13 rhetoricians to carry forward this debate. Today, before we begin the program, we have our principal, Dr. Hari Vasudevan, speaking a few words, followed by the guest of honor, Dr. Valentina Bala. Sir?
Yeah.
Principal,
thank you, sir. Thank you.
Yeah.
Good afternoon, Professor Valentina. Thank you so much for joining us from Romania. So, the participants in the FDP, as Professor Dr. Sunil rightly said, and potentially we all understood the importance of AI, of which we are actually going to get into in our next 6 days through this online FDP. Today, everywhere, everybody's talking about artificial intelligence and different domains of technology being influenced by artificial intelligence is making a difference due to the computing power of machines, due to the algorithmic advantages, the advancements in algorithms and all that. Everything is all about artificial intelligence today. So a lot of engineering, even undergraduate programs have come up. So therefore, faculty members belonging to whichever field it may be, there is a need for them to get updated with some kind of exposure to artificial intelligence and machine learning. And machine learning has always been there in electronics and telecommunication. In your field, I'm not from your field, but I know in your field it has always been there. Now it is there with more robustness, more strength, more of a stronger push, because the emerging area technologies, the allied technologies are making a difference. So therefore, for us, the teachers, it's very important now to get tuned to some kind of learning beyond the normal conventional subject, because some of the technologies that we have been using in the area of electronics or electronics and telecom may not be so relevant unless we take the help of AI tools for processing and other aspects of business or wherever you apply these tools to. So in that context, the Department of EXTC took the initiative of applying to All India Council for Technical Education for an FDP like this, that is CrossRoads of AI and signal processing. I'm happy and thankful to AICTE for accepting our request and sanctioning as this online FDP. Good to know that there are a good number of participants who are attending this faculty development program. So over the next 6 days, I'm sure 2 to 2.5 hours of learning and interacting on this topic will really help all of you gain rather much more stronger insights into the field. Signal processing, image processing, and all most of you have been doing, but with this AI and the power of machine learning, I think there'll be more clarity that's coming, because this kind of exposure is really needed, as I mentioned earlier, when you are tackling students' problems, different projects, when you are guiding and mentoring them on various projects, whether it's a smaller project or a bigger project in their final year, this kind of knowledge and exposure is really required. So in that sense, I'm very happy to note that this FDP is happening now. In fact, in last 1 month, this is the 4th faculty development program that's being organized by our college. The 4th such ATAL FDP sanctioned and approved by the All India Council for Technical Education, New Delhi. So thank you to the AICTE team that has sanctioned our request for conducting this FDP. In fact, 4 of it, this being the 4th one. Thank you to the department and congratulations to Dr. Sunil Karamchandani, coordinator of this FDP, and also Professor Ranjusri Pal, the co-coordinator, for taking the initiative. And I'm told by Sunil sir that there is a team of teachers, Vivek and a few others in like Deepthi and all others are helping out. So thank you and big congratulations to the entire team of people who are working on this. And I'm sure there'll be many takeaways for you at the end of the 6th day when the FDP concludes and when we have the validity function. At least my expectation is that it will rekindle the quest in you to pursue this area of technology more vigorously. That could potentially be a major outcome out of this FDP. So congratulations to everybody. And today teachers' job is not so easy. Teachers have to keep getting updated very often because students in the classroom are aware of what the teacher is going to discuss because of the information-driven era and various tools and programs and courses that they all have at their disposal through various channels. So therefore, when the teacher is teaching there, he or she will have to go one step ahead and deal with the students by making them get involved in the subject. So to have that upper hand over what students already know, constant updating is really required. So these kind of FDPs, I'm sure, will help teachers look at these aspects more seriously. So thank you very much, Professor Sunil, Professor Anjushree, and the entire team of our teachers in the department. I take this opportunity to also wish all of you all the best. So have a great time over next 6 days of this FDP. Thank you very much and all the best.
Thank you, sir. Now I request Vice Principal Dr. Narendra Shekhokar to just speak a few words.
Yeah. Good evening, one and all. So it is really great initiative which is taken. Am I audible?
Yes, sir.
Am I audible? Yeah,
Yes,
it is a really great initiative taken by EXTC department to organizing FDP with the recent trend. Okay. So That's really great that this FDP inauguration is honored by Professor Balan from Dr. Harivasudevan sir is also there, and great initiative taken by Dr. Amit, Dr. Sunil Karamchandani, and entire EXTC team. Thank you very much.
Thank you, sir. Thank you for your kind words. And now for the guest of honor for today, Dr. Valentina Balas. She has an extensive array of accomplishments to her credit, but I'm just giving you a brief glimpse. She's currently a full professor with the Department of Automatics and Applied Software, Faculty of Engineering, Aurel Velasco, University of Arad, Romania. As part of her industrial laurels until 1993, she excelled at Scientific Research Institute of Railway Cars of Arad, then found a career with their Air Navigation Protection Service. Her translation into academics resulted in authoring 120 books, 25 book chapters, and more than 60 edited books in Springer, Elsewhere, and CRC. With more than 350 scientific papers in conference volumes, Val has given more than 60 invited lectures, you can't beat that, around the world, India, China, Japan, Taiwan, Singapore, USA, and a lot of other countries. I can't stop naming them. She was recipient of the Vice President Awards of the IFSA International Fuzzy Systems Association from 2013 2015, member and head of multitude of professional bodies, including a senior member of the IEEE, general chair of SOFA, the Workshop of Soft Computing and Applications from 2005 to 2016. Because that is where we met. Amongst her many achievements is a collaboration with meeting Professor Lotfi Zadeh for the Unverse, the founder of Fuzzy Logic and Soft Computing, and one of the giants of control, AI, and system science theory and engineering. She single-handedly is instrumental in bringing fuzzy systems popular in research circles in all of Eastern Europe. Please help me welcome Dr. Valentina Bala. Dr. Valentina?
Yes, I am here. Thank you very much, and good evening to all of you. Here it's an afternoon. First of all, I would like to express my appreciation to organizing committee and especially to our good friend Sunil Karamchandani, who invited us in this faculty development program. I want to tell you that I visited your beautiful city in 2014, and Sunil visited Romania in 2015. He visited our city for giving lectures, and also he was involved in a conference in a city near Arad, in Oradea, and he visited Oradea University as well. So our friendship, it's quite longer than 10 years. Anyway, I visited many times India, more than 20 times, and quite all region. And I can tell you that I appreciate very much your system of education and your students that are so well prepared. I am collaborating with many professors there, and we are writing together books, articles, and try to have even project from European Union side. We try just nowadays. My congratulations to Sunil for this wonderful faculty development program under the name of CrossRoads and AI and signal processing. That is a very hot topic, and for students that are here in this conference, it's a very important fact that they can be together with good specialists that Sunil invited along a week. I have prepared some words if I still have some time. Is it possible? Yes.
Yeah, please go on. Yeah.
Dear colleagues, dear students, ladies and gentlemen, I'm pleased to speak as chief guest as the inaugural ceremony of faculty development program. And I'm speaking to you as a person trained as an engineer, but in some ways fulfilled as an engineer because I got the practice real engineering. But throughout my life, in all the things that I have done, I have always valued the training I had as an engineer. It has shaped the way I think and approach problems and try and bring solutions to them using scientific knowledge and applying practical principles to try and address the issue that we face. Science and engineering are intervened disciplines. Science involves examining, studying, and understanding basic phenomena in the physical and natural world. Discovery is the essence of science. Engineering involves applying the knowledge about these basic phenomena to design object, process, and systems to meet real-world challenges in society. Science and innovation is needed for engineering, while engineers need to explore the frontiers of science to solve engineering problems or develop new technologies. I studied electronic engineering, automatic control systems, and systems engineering, and subsequently software engineering. And those principles remain the same. Whether you are trying to program a computer on the front face of the computer using machine language and an assembler, or the high-level languages that we use today to design massive computer systems, the thought process and the engineering behind is all similar. We need to understand science and engineering so that we can deal with the problems that we have in objective way. If we are unable to understand science and engineering, and we don't understand what is happening, then the solution that we propose, the solution that we want to adopt, will not be practical, not affordable, not achievable, and in the end, will not just fail us in our own cities and countries, but also fail us on a mass scale as humankind. So we need science, innovation, and engineering to help us to solve these problems that we have. Of course, artificial intelligence is on top of all research nowadays. I would like to acknowledge the contribution of all engineering around the world, of all speakers that will be in this faculty development program, and to all our professors who have contributed to training our engineers. As the world continues to face increasingly complex challenges like climate change, pandemics, digitalization, we need good engineers more than ever before, good engineers who appreciate the disciplines beyond engineering and understand humanity and how we can make cities not just livable but lovable. Let us continue to apply science, innovation, and engineering and artificial intelligence to bring ideas to life, create solutions to real-world challenges, to turn our dreams into reality, and to push the frontiers of what we know and what we can achieve. Thank you very much. I wish you good success for all participants along this week, and I'm sure that all the students will be very happy to have such good speakers that Sunil approach in this faculty development program. So congratulations, Sunil, and congratulations, Professor Ranjushree Pal from the Department of Electronics and Telecommunications Engineering.
Thank you, Valentina. Well said.
Thank you.
It is always science for humanity, and that I think should be the goal of ultimately all the engineers. And also, sir, you'd be glad to know that one of our students is also ex-students is currently also working closely with Valentina, helping her in her publications and also reviewing papers. So
Very good, very good.
teacher
Thank you,
Sanghvi
ma'am.
has an involvement with the University of Arad in one way. Yeah.
Thank you.
Yeah. Thank,
I'm happy.
thank you.
Thank you. And the invitation to visit our country, to visit our university, and to collaborate, to be together. Good luck.
Thank you. Thank you very much, madam. Thank you so much. Yeah. Now I think we will begin with our first session for today. We have online our keynote speaker, Dr. Marius Bala. So I would like to introduce him before we hand over the mic to him. Dr. Marius Balas is an IEEE senior member, habituated professor at the engineering faculty of Aurel Velasco, University of Arad, Romania. His research topics are in electronic circuits, system engineering, intelligent and fuzzy systems, adaptive control, modeling, and simulation. He is the author of 17 books and book chapters, 120 indexed papers, and 7 invention patents. His main scientific contributions are fuzzy interpolative systems, passive greenhouses, intelligent rooftop greenhouses, water variation, constant time to collision traffic optimization, and PWM inverter for railway coaches in tropical environments. He is also the coordinator for several research projects and student competitions, co-organizing the Control, Engineering and Applied Software Department at the Engineering Faculty of Aurel Velasco. A good friend and a great host, presenting Dr. Marius Balas. Marius, now it is up to you for the keynote session.
Thank you so much. Do you hear me?
Yeah, absolutely. Yeah, absolutely. The mic is all yours.
Well, honored audience, I want first of all to use 5 minutes to present our university, our town, and our specific our specialties. So you see, Arad, it's our town. Astra, it's one basic company, railway coach company that is linked to the history of our town. And here it's SOFA, the international conference workshop for soft computing and applications, which is under the Aurel Vlaicu University's cover, let's say. So you see here, it's the map of Europe, and Arad, it's in the western side of Romania, very close to the Hungarian and also to the Serbian frontiers. And here it's Google Map image of Arad. Here it's the center, but here it's most part, not all, the most part of the automotive companies that are making the object of my presentations. Of my presentation. Here you see some companies that are hosted by our town. Well, let's say, for instance, that the most well-known could be, for instance, Joyson Safety Systems, former Takata, Leoni Wiring, Webasto, Yazaki Component Technologies, Coffee Cab. So they are mostly producing parts for automotive industries. There are chances that your steering wheels or belts to be produced in Arad. Here are those companies that west park of Arad, and here is some facts about our history, which are important. History is important because it can show some knowledge, some experience that is helping you when tackling new projects. Experience is not. It's important. Here you see the first outside. Now, can you see my screen?
Yes, sir. We can see your screen. Yeah.
Okay. Thank you. So here are some projects, some products of Arad. You see, This was the first automobile which was made in Austrian-Hungarian Empire, but it was made in Arad in 1909. And here are tramways, metro, subways, or railway coaches produced today. Now, it's an inside of such a railway coach, and there are some citerns, some freight cars that are produced equally in our town. And here it's there are some test coaches. You see, wagon laboratory. It's a laboratory wagon, and so we are. Or now I'm not working there anymore, but we are still testing the rolling stocks on good conditions. And here is traditional Friday beans. Well, it's a food for the people who are working in the tests. Here it's about SOFA. SOFA, the International Workshop on Soft Computing Applications, and here are some images linked to SOFA. Now I can start my presentation, my proper presentation, which I'm afraid will be a little bit different of what are you firstly interested in, because first of all, because our specialty is rather linked to hardware than to software, and then it's because in this stage of development of IT, the hardware is beginning to gain some positions. Well, there is a very simple argument, of course. Now in our days, when the code can be written automatically, well, of course, with in a certain proportion. On the hardware, we cannot do the same. So hardware is continuing to remain more linked to the human brain developments and ideas. And what is still very important is that we are now facing some fundamental problems, development problems that are, first of all, they must be recognized. They must be approached then to find solutions for the future. And one major problem that I think we have to deal with, it's the parallel shift. And the parallel shift has the power to accelerate and to improve the signal processing among many other domains. So this is the content. Well, you see, the first section, it's about Moore's laws, Moore's laws, which is, it doesn't seem to be very connected at the first glance with the subject, but you will see that it's interesting. Then parallel versus von Neumann architectures. This is something essential, very important. Then FPGAs and HDLs. So we are approaching to the technical solutions. And here it will be a section which I think it's very important for any engineer in any field. It's about systems engineering and its main tool, the top-down approach. Speaking with Professor Sunil, well, he said that you don't have in your curricula systems engineering. So I think it's a good point to discuss a little bit about this and about the main ideas that are very useful in these years. Then the parallel shift. We'll talk a little bit about the parallel shift. Conclusions are very short. Now about the Moore's laws. Well, you know, Gordon Moore, it's well known. It's a personality in the IT and especially in electronics. And well, he was a young member of the Shockley team, and then he moved from Shockley, who was not a very gentle chief. He moved to Fairchild, and there they realized the first integrated circuit. And then he moved again and founded the famous Intel company. So he was one of the minds that had a very important impact on electronics. Well, he died recently, and he was known first of all because of this first law that he formulated. Now, that law, which states that on the same surface of silicon, the number of transistors that can be integrated doubles each 2 years. That is not the first formulation, the second formulation of his law. The first was a little bit more optimistic. He was assuming that this number of transistors will double each year. Then he made the correction, so it's 2 years, not 1 year. But anyway, it's an exponential growth. And here you see that, in fact, his idea just generated a lot of research and a lot of some assessments of the engineering fields and the economical field, and they discovered that this law it's applying. Well, it's not a very precise law; it's a thumb law, how it's said. But you see here a lot of elements that are, in fact, they are early than 1965, 64, when Gordon Moore exposed his law. So it seems that this exponential growth, it's a characteristic of the growth in general. So human technologies and human knowledge were growing like this for many years, from 3-4 centuries at least. And what is interesting is that this development, it's keeping its pace. It's not getting slower. Now, what happened after 1965? The chip makers deliberately choose to stay on the Moore's law track. So they decided, well, in a tacit way, perhaps, to follow this this law, and this strategy is called more Moore. Well, more Moore means that we are trying to follow this exponential law, sometimes forcing it a little bit by economic leverages, for instance. Only what happened after many years, yes, many years, in the last decade, the Moore's law began to be doubted. So you see here a statement: the Moore's law closes to its limits. So this is something important for electronic people, of course, but for all the industry, because it means that our development in the close future will be limited, and we will lose our pace, and we will lose some of our achievement, even economical. So you see here, I found a paper, a very recent one, about the Moore's law. Further progress will push hard on the boundaries of physics and economics. This will is connected, of course, with you must think that that this is connected with supercomputers that are supporting artificial intelligence. So what's all about? You see here why the Moore's law it's closing to its limits, because reducing continuously the dimension of transistors brought us to the nanometer domain. And you see here there are some figures about how are looking different technologies: 10 nanometers, 7, 5, 3, 2 nanometers. So 2 nanometers means the channel of a transistor, of a MOS transistor. So you see the areas are continually decreasing, but we get to a point where you must, this is obviously a limit, a physical limit. 2 nanometers is barely the width of 10 silicon atoms. You see, so you cannot make a transistor with 1 atom. Well, one can make transistors, and this is a rather old communication, of a molecule, a certain molecule of phthalocyanine, surrounded by just 12 indium atoms, constitutes the smallest possible transistor which was realized so far in laboratory. Of course, these are the coordinates of that paper, and the gate size, it's just, you see, it can work. This transistor, it's called 1 electron transistor. It can work with 1 electron, but obviously this is a limit. So can we have some alternatives to this? Can we hope that the artificial intelligence will get the necessary support from hardware to continue its growth. I'd say that just a second. I will give you the response to these questions in 2 slides. Now, I added here some slides to present the current achievements of the electronic industry and which are the technologies that are supporting the famous 2 nanometer technology, which is now our objective for the following years. They are made in laboratories, but these technologies are producing integrated circuits that are used in our phones, for instance, smartphones. Now, novels from Europe, I don't know if you are aware of this. There is a company which is seated in Netherlands, ASML. You see there some facts about this company. It has branches all over the world, in Bucharest included, and this is the only company in the world that can realize the photolithographic setup for such small dimensions of circuits. So you can imagine that at such dimensions, look, for instance, the wavelength length of the far UV light. It's 100 nanometers, and we must produce some masks and to make photograph engravings at 2 nanometers dimensions. So this can be done only with lasers, with very precise far ultrawave lasers, and with optical, with some optics that are far beyond any other comparison. So ASML can do this, and it's the only company that is producing such technologies, and they are also selling in Taiwan, in any country that is involved, in South Korea and so on, and they are also cooperating with Carl Zeiss for the optical lenses. And here it's the most important news for this field. So the leading company for the time being, it's Taiwan Semiconductors Manufacturing Company, TSMC. So you see, USA, for instance, is it's not in the first range. It seems that Taiwan it's beginning to become the first actor, even comparing to Samsung. So what is doing Taiwan? It's opening this very year in Phoenix, Arizona. The first idea was to do this to make these plants in Ohio, but they moved in Arizona. there are two plants, one for 4 nanometers and the second for 3 nanometers. But what is more interesting is that there is a plan, a schedule to produce to finish a plant for 2 nanometers, the real 2 nanometers plant, in 3 years from now on. And this is an investment of you see $65 billion, but it you know in these actions the budget can increase down the lane, and which is the goal, the technical economical goal. It's that this technology, 2 nanometers, will bring 15% speed comparing to the existing one, and the consumption will be also reduced by 1/4. So that is the landscape of the hardware in the following years. Now I was talking about more, and we were asking ourselves if there are alternatives to more, and here it's the alternative. It's again linked to Gordon Moore. So the new law, the new strategy, it's called more than Moore, not more than Moore. Here you see a link and the coordinates of a short article about this subject, and the idea it's it's very interesting, and it's coming. You will see in several slides. It's coming rather from system engineering approach. So more, it's about miniaturization of the main circuit of the processor. So that is the main concern, and the idea was that if the if the processor is very performant and very well dense and very loaded with transistors, it will be better than others. But more than Moore changes the focus. It changes the focus towards the whole applications, not only to the essential part of its application. It's trying to assess the whole application, even the sensors. The sensors can improve a lot the performance of an application, and can in the end, what is interesting for us, it's the final performance of the whole application, not the fact that the processor is very good, but the sensors are not so good. It's not pleasant, no. It's not good. So you see here, more than Moore means to turn on whole application and to assess the performance in a holistic way. See, so this is typical for system engineering. Now about let's talk a little bit about the more than Moore strategy. This is a text that is explaining more details the idea. So more than more changes the focus from the level of the electronic device, so microprocessor, microcontroller, DSP or FPGA, to the whole application level. Rather than making chips better and letting the applications follow, the designers apply a holistic top-to-down approach, starting with the application and correlating all the application components, sensors, power management circuits, and so on. So you see here, it's a brief presentation of the devices that are all involved in the more than more strategy. So the designer have to be careful, all of them, not only to the processor, to the main processor. So you see here in the center are the materials, which some of them are new or well, rather unknown to people that are not involved. In the middle are the components. Well, the components, and here are the domains in where more than more is applied. It's taken inside today. Telecommunications. So you see 5G antennas and optical sensors, optical networks. These are under research, and there are already applications, a lot of applications for them. In automotive, which we like in Arad, we have the accelerometers, the LIDAR, and the radar. In the entertainment industry, there are a lot of applications for more than more. Lightning displays, and here it's augmented or virtual reality, you see. And about the energy, again, there are some applications that are taking into considerations as a whole application, as only one application. Which here you see, well, I must confess that these are some components or devices that I'm not very familiar with. They are very new. Vertical cavity surface emitting lasers. These lasers are able to emit those ultraviolet radiations that can be used into the engravements. Here it's the photonic integrated circuit. We must expect in the following years to some revolutions in the computing technologies. One of that possible revolutions, it's about the quantum computing, which frankly, in my limited and humble opinion, it's doubtful a little bit. I'm not very enthusiastic about this, but the photonic integrated circuits, they have a potential that is more like to be more practical, because this, you see, this technology, it's very much suited with the silicon leading technology of today. Well, silicon is transparent, and you can make lasers, as you saw here, And well, who knows? But this we can expect in the following years to break the balance and to produce spectacular advances. Now, since I talked about Moore law, you see here there are more Moore's laws. There are laws, several laws, which initiated from the first Moore law. They are very popular, in fact. You see here the Moore's law for knowledge. It was formulated in 1981. The general human knowledge doubles every 12 months, every year. This is something essential, and this is very dramatic for our educational system, because you see the knowledge is increasing exponentially. Well, why the human mind it's not sure that can follow this pace. Some people, very gifted people, can keep the pace, but for the whole community, this is a problem, and we are now facing scholar drops from many students leave the system because it's too much for them, and we must revisit our knowledge way of representing and of managing, and we must decide nowadays what is worth teaching and what is not so important and can wait for deeper studies. And this is a very important issue. I think you're facing it even now. Now, there is a Moore law for everything. Can you imagine? So this is addressing the whole society. What I was talking about the Moore's law for education. Well, this Moore law for education, it's a little bit more difficult to apply. In 2001, Gordon Moore was complaining it's hard to come up with ways to increase productivity in education. And that is why I think the education, it's very important. It's essential for the future, for our future. And we must find ways to improve the performance, the productivity of education, if I can say this. Luckily, people are beginning to be aware of this problem, and you see, I found a paper, 11 years old, where the author George Anders says that one can observe that Moore's law is making its presence. I can give you a good new. It's not new. It's old. It's a new fact. In 1979, I think you know about the Club of Rome, and in the Club of Rome, it was a report which was authored by Botkin Elman-Gira and Mircea Malița, who was Romanian, and that is why I was interested first to read this paper. It was, you see, I was a student at the time, and this paper states that in a world where all resources are limited, space, time, raw materials, you name it, all resources are limited, there is one remaining resource that it's virtually unlimited, and this is the education. Yes, so the education can find in itself resources to continue development, to continue improvements, and to break barriers and obstacles. Yes, but it's not given. We must fight for it. It's not coming from the heavens. Now, I found something. I don't know if you're interested in these observations, but they are explaining the strategic situations and the evolutions, and I think it's still interesting to talk about them because they are affecting our fields. Now, the problem that I'm presenting you now, it's the relationship between the global financial crisis, but you see that global financial crisis from 2008, it was one, but crises can come, and they are coming and going. And what is the effect of these laws, of this crisis over the development of the society and of the technology? And I found something very interesting and even, let's say, optimistical. Why? As we were looking for facts about the global financial crisis from 2008, I found that contrary to the very common sense idea that during financial crisis industry weakens, I found that IT and electronics were not weakened. They were witnessing revolutionary developments. I will talk a little bit about the Marceller group, which was the typical example for this effect. But if you want to look around to other fields, you see the the electrical vehicles, for instance, Tesla, were breaking immediately after the crisis. So what is the mechanism here? High leverages before crisis gave high profits, but allowed the owners of the borrowed capital to influence the granted technologies. Now, for instance, in electric vehicles, I go to a bank to ask money to develop a full electric vehicle, and the bank was already giving some money to oil companies, and they don't want that oil companies to lose positions too much, and they are telling me, okay, we will give you twice the money you asked, but for hybrid vehicles. See, so they have the power to influence your technologies and your ideas, even if sometimes these influences are okay, but not all the time. The after crisis, perhaps it's giving low leverages, but the owners of equity have the chance to choose their own objectives in a total freedom on a better technical foundation. So it means that a company like Nissan, for instance, developed on their own money what they needed, they wanted, the full electrical vehicles. Or in our field, in the line of our presentation, Maxeller technologies were able at that time they didn't obtain money from banks, so they tried to develop to activate their own resources, and they developed a full parallel technology. That was the moment, okay? And why this is good? Because in the end, a better technical foundation is rewarding you with even money in the end, and with a better technology that is working for all people. So the global financial crisis didn't stop IT, but on the contrary, that's good. Now we must talk now to focus on more technical aspects. I was telling you about parallel versus parallel must be compared with von Neumann architectures. I think you perhaps know much of what I'm telling. In this case, I'm demanding excuses. I'll try still to bring some facts in later on. Now, the von Neumann architecture is built around a famous bus, data, addresses, and control bus. The program's instructions in a pure architecture used to use the bus one by one for the instructions, for all the 4 steps of the instruction cycle: fetch, decode, execute, and write back. Except decoding, all the steps demand complex bus traffic and operations, which creates a fundamental limitation of the computer speed. The entire central processing unit must wait for the current instruction to complete before proceeding to the next instruction. Well, this is very flexible, but it's not fast at all. It's very slow. So this problem was addressed in time. Caches memory, pipelines, different parallel architectures were developed in time, such as multi-core. This is very popular, multi-core architectures. And all these approaches were trying and are trying to address the major drawback of the von Neumann architecture. So if we cannot, we still need a bus, we'll make several buses and several kernels and a lot of cores. And this can work in a parallel way. Well, it's not full parallel. It's half parallel. Let's see. But first of all, I was addressing the chat GPT to find the most illustrative parallel architectures that are now in the field. You see the symmetric multiprocessoring, multiple processors that are sharing a single memory space and are controlled by a single operating system. Massively parallel processing, many independent processors. This is something known, each with its own memory working on different parts of a problem in parallel and communicating through a high-speed interconnection. Cluster computing, grid computing, distributed shared memory, graphics processing units, vector processing and multi-core processors are such architectures that are working, are emulating the parallel, and some have some elements of parallel operation. Why? This to accelerate the final application, to avoid that bottleneck of the von Neumann architecture. So I think that you probably know much more than me in this field, because it's parallel computing. It's part of your curricula, and well, they are interesting, all of them, good ideas. Still, something is not okay with them. Why? They are not purely parallel. They are preserving parts of the von Neumann architectures. So in the end, the performances are not the best possible. Here you see the full parallel architecture. This is purely parallel. So this is the field programmable gate arrays, FPGAs. These are integrated circuits that can be programmed to perform specific tasks in parallel. They are highly flexible and can be reconfigured for different applications on field. So one of the advantages of this system is that you can program, you can configure the application on field, and which is even more interesting, they are accepting the dynamical configuration, so you can change, you can move from different architectures even during the operation. So what is FPGA? You see, there are not many elements, but there are many of them. That is the main idea. There are only 4 basic elements: input, output pads, okay, what's logical, and then the main logical element of this kind of circuits is the logic block. But these logic blocks, LBs, they are programmable or even configurable. You will see in the next slide. Then what is typical for FPGA? For an FPGA is that the logic blocks are emerge in a network of connections. It's a connected grid, connecting grid that enable us to connect each logic block we want, which any other block. So this is done by means of a switching box. You will see in the next slide how are they operating. Now, first of all, the logical block, it's configurable. You see here they are configurable by the way of nature of lookup tables. There are lookup tables, and these lookup tables can be configured. It can realize several logical functions, not only gate. Well, the starting point of this these architectures, that was the gate areas that were produced in the 70s and 80s. They were configured, they were using, let's say, NAND gates or NOR gates. But here we can use several loads, several operations, not only NAND. And about the switching box, this is the typical FPGA concept that was introduced by the FPGA. You see here how it's operating the switching box. There are 4 wires. They are wires, not nothing else. 4 wires, and they can be connected in several ways. You see here we have 1, 2, 3, 4, 5, 6 switches. They're transistors, MOS transistors, MOS transistors, and we can connect. We can make all the desired connections: up, bottom, left, right, up, left, up, right, bottom, left, bottom, right. And when a transistor receives at its gate the command, it's just opening, it's just connecting those wires. Not the others are not connected. And how we work with this? The main concept that is describing, and it's which is stands at the base of such a application, is the net list. The net list is a list of connectors of instances, and for each instance, a list of the signals connected to its terminal. So that net list, it's just a setting of the whole programmable switches in the circuit. By this net list, we can create any links we need in order to produce the application, the desired application, out of a generic network, gate network. Why this system it's interesting and it's important? Instead of programmed operation, FPGAs exhibit a programmed architecture. FPGA is a simple electronic circuit, not a computing system. The FPGA connecting system is, in the same time, programmable and wired. This is fundamentally accelerating the FPGA performance because its programmable wired logic, issuing out of the gate areas, is able to work fully parallel. Yes, and what is important for artificial intelligence is that this kind of architecture is very much close to the brain structure, which is parallel. Yes, all the neurons are working in parallel. So for Neumann architecture, it's left behind. But this is not very simple to work with, and it's I would say you will see in short time that we need a new generation of programmers that will exploit these resources in the next years. Now, what is telling ChatGPT about FPGAs? I think it's interesting to ask its opinion. FPGA is true hardware parallelism, allowing multiple operations to be simultaneously executed. Unlike traditional Neumann processors, FPGAs can be configured to perform multiple tasks in parallel without the need to fetch instructions. So we are not anymore programming the operation. We are programming a circuit, a pure electronic circuit that will operate in the way we want. And about the applications, the original application, the original let's say genesis of FPGA lies in the rapid prototyping. The rapid prototyping of VLSI circuits, very large scale circuits. Being very complicated, VLSI needed a lot of efforts to develop the masks, but the smallest failed, the smallest shortcoming of the design was just ruin everything, the project, and you had to take it from the scratch again. So the idea of the rapid prototyping was that let's make programmable circuits that can be reprogrammed, that can be reset, and only when this prototype was testing positively and it was okay, only then they were switching to the VLSI mask and production. And so for a short time, that was the leading idea, but in the end, the VLSI circuits need a lot of, they are effective only in large scale, in mass production. And very often people realize that there are most of applications are not large scale, and FPGA could be used as a final solution for a lot of applications that were not large scale. So they started from the rapid prototyping, but FPGAs became the leading solution in many applications. Now, about the digital signal processing, FPGA can handle complex mathematical operations in parallel. That is ideal for the signal processing task, and you can appreciate this. That well, if you work in parallel for displays, for instance, or for I will give you some applications in short time. This is gold. Yes, for digital signal processing, the parallel, it's the future. It's a more than Moore solution. In data acquisition and processing, FPGAs can process large amount of data simultaneously. Imaging medical imaging or aerospatial from satellites, scientific research. You will see seismic mapping of oil reserves at sea. Brokerage banking, that is a very interesting story. I will tell you in 2 slides about Maxwell and JP Morgan Chase, and so on. And text parsing and image video processing Again, the parallel nature of FPGAs allows for faster processing of text, images, and videos, and they are largely used today. Now, let's move to the FPGA and the way in which we use them. I must check a little bit the timing. I have at least half an hour, yes? Well, the first FPGA were military, aerospace circuitry. It was a company called Xilinx that issued in 1985 the first commercial FPGA that was addressed to the military applications. In fact, aerospace remained one of the first vector of the FPGA industry. So I could say, according to my knowledge, most electronic circuits in planes today and in space are FPGAs because they are flexible. They can be programmed on field, and they can be interchanged. You have a number of boards, and if something gets wrong in your plane, you'll go and change the damaged board with a new one, and just write inside the program, the correct program, and that will work. And on the there are some families of FPGAs that are specially designed for aerospace, in which there are some redundancy. The redundance principle is used. So if a hard particle it's hitting gate or two gates or three gates, they can be replaced by the help of the dynamic reconfiguration, and you will even not notice that your equipment was damaged. Well, to understand, perhaps I have here a little another image, another approach of the FPGA. You see, since transistor logic, TTL integrated circuits were realized starting from gate areas. They were made by wired connections, mask programmable circuits. FPGAs just replace the rigid wired logic with a network of nodes composed of microprogrammable driven switches that create a reprogrammable interconnection system able to configure or to reconfigure the desired logic circuit. So this is programmable. FPGA is like a breadboard whose wire jumpers are replaced by software commands. That is perhaps the most synthetical approach. Now, how will we work with FPGAs and with other, of course, with other digital circuits? In fact, with all possible digital circuits, it's a special language that I think you know about. It's called Hardware Description Language, HDL. Now, HDL was again initiated by military. The first version, the first approach was called Verilog, and it was Prabhu Goel and Phil Morby. I think Prabhu Goel was Indian, and they developed the first such language, which is called Verilog, and which is purchased by Cadence Design Systems. Cadence is the leading company that can take a project in HDL and transfer it on silicon. And you see, in 1987, the US Department of Defense initiated a new version of, which is called VHDL, Very High Speed Integrated Circuit Hardware Description Language. And thanks to VHDL, all military equipment, no matter its producers, could be treated in the same optical manner. What is interesting for this VHDL is that the development and the conceptions and the standard which described VHDL was transferred to IEEE. This is one of the major projects of IEEE, and it's still working today. And it's they are standardizing VHDL. But VHDL and Verilog are very close to each other, Verilog close to VHDL, and nowadays they are very interchangeable, and we just have some problems, applications with students, and they could switch from one to the other very easily with no issues. Here it's one of the such boards that we can work with the students. This is a very cheap one. You can see only $185. But there are some changes here. Xilinx were for a long time the leading company in the field. And now they merge with AMD. So this is a new approach. But anyway, the schema is the following: Xilinx and AMD are USA, but they are producing their circuits in Taiwan. Here, I will show you two applications that we made in our university. There were some projects for bachelor degrees. Here, it was interpolator. It was a fuzz interpolative system that was developed in FPGA some time ago, and the elements are, well, the stages of development. Of course, they are starting from a schema which can be transferred automatically to the code. You see IEEE there, so it's under IEEE standard, and then you develop some internal schemas for the FPGA, and you can test this schema, and you can also optimize the way in which the surface of the silicon is used, or the way in which the heat is produced, and to avoid concentrations of heating processes only in small areas. And in the end, you can obtain that program that can be transferred to the board, and it will operate strictly like in the simulation. So these are some some pictures. As you see, there are 2 applications. Well, you can practically do whatever you want. It's very flexible, and students like to work with this, but very few manage to properly realize an application. I can tell you that at least in our university, we are so small city, and we have not so many. We cannot not a selection base for students, but out of 40, 50 students, 5 or 6 are able to finish a project and to put something on the table, but not very important projects. Now, what I want to, I think it could be interesting for you, and which is rather my favorite specialty in these years, and which can help you, I assure you, it's the system engineering. And the system engineering is providing the famous top-down approach, which should be applied whenever you face a complicated or a large-scale application. Now, system engineering it's an interdisciplinary engineering field focusing on how complex projects should be designed and managed over their life cycles. The very idea of the life cycle of a product, it was belonging to the system engineering. You see, this concept has originated from 2 very important leading institutions. First, Bell Telephone Laboratories, which in fact they invented the electronics. That is the truth. Bell invented electronics, and you see here Wade Bode and Harry Nyquist for people in automated control. These are, like, how to say, ABC. And the famous Claude Shannon, the genial Claude Shannon, who was in 46, he was the first to describe and to formalize the concept of information. And Bell Laboratories started, and then NSAA, NASA, we called it in Romania, and the USA Department of Defense was taking the relay and advancing. This guy is a controversial figure. Perhaps you know about him, Werner von Braun, but he was the mind that created NASA as we know it, and who put a man on the moon, not only one, 4 missions, I think. So they embraced this idea and developed, and it's their belonging. You see here, I put here some system engineering definitions, but there are many definitions because the concept is very complicated and it's very vast. And you can see, you can look at it from different directions, and it's more and more, you look at it, you find new traits, new features. So these are just to illustrate that the concept it's complicated. What are the main sources for modern sources for system engineering? There are the 2 NASA NSA systems engineering handbooks. The first one issued in 95, and it was very, I would say, systematic and very condensed and very clear and very simple. And then the last one, it's on the contrary, it's very comprehensive. It's very vast, and it's describing all the way in which NASA is organized and how they are tackling the programs and how they are dealing with projects. But these books can be found on the net and are very interesting. And I think each engineer, even programmers, will discover interesting knowledge inside. Now, about system engineering, what is interesting here is that it's relying a lot on the graphical representation of architectures and information flows. It's very graphical. You remember when I told you about the Moore's law for education, Moore's law for knowledge. Knowledge is increasing with an exponential rate. A way in which we can address this large amounts of knowledge is their graphical representation. Our mind is very much based on the sight, and these representations can transfer a lot of more knowledge than text itself. So that is why system engineering is very much related on graphical representations, and there are some classes of software specially dedicated, which can be used in an application, but they are issuing out of system engineering. One of the most popular is the UML, Unified Modeling Language, and I think this is very interesting. Let's compare software and hardware. I belong to hardware. I'm just looking at the software and have links, of course. But in my perception, hardware has an advantage because they are more not so proud, let's say more humble. And when I was telling you about the hardware description language, hey, you know how many HDLs are existing? Just one. Why in software you can develop software description languages? Yes. And they were developed, of course, but there are several of them, and it's not clear what is the leading one and which is the most recommendable for applications, because people in software are more mathematical, more abstract. I think perhaps it's one explanation. But anyway, what is bringing system engineering? It's the holistic view. Yes, a system has to be saw as a whole, and this approach can differ a lot from the sum of the parts properties. So system engineering is embracing the holistic view that is typical, and that is what I try to show you when talking about the Moore's laws and the parallel shift. Again, and in the second hand, system engineering is interdisciplinary. So engineering, management, economics, world knowledge, everything. The typical approach is top-down, which is offer us, of course, less details. There are no miracles, less details, but more comprehension. And we can, thanks to these comprehensions, we can spot, we can identify, for instance, synergies, which are helping a lot the applications. And I will give you one example, with one famous example that is standing in the first row when teaching system engineering. It's about the Sendai subway, which was developed starting from 80s. And this is the network of Sendai. Sendai, it's a town in Japan, northeast of Japan. It's in the Gulf of Sendai. That was the Fukushima. Fukushima nuclear plant was providing electricity for Sendai mostly. And what is this metro so famous? Because they developed for the first time in the world a network with very modern Hitachi wagons, which has reversible converters and regenerative braking, because they were using for the first time GTOs, gate turn off thyristors. The energy consumption were reduced by at least 25%. But what happened? The first stage, the first leg, the network was working very nicely. But then, as the network was extending, some phenomena appeared, very disturbing. When two or several wagons were braking simultaneously, they had tension overload, and the protection was on, and everything was stopped. In the same idea, when several wagons were accelerating simultaneously, it was a current overload. And then again, the protection over current protection were fueled. Now they lose a lot of time until our friend and mentor and guru Michio Sugeno managed to find a solution after 2 years of efforts. And he solved this problem thanks to the fuzzy logic, and that was initially initiating the famous fuzzy boom in Japan in those years. And what was the idea? That very good wagons are not working properly when together, but what you can do, first of all, they prolonged they were prolonging the acceleration and the braking times, so that were leading to smaller currents. And most important, no, they drop out the precise schedule. The idea was to synchronize a wagon that is accelerating with another which is braking. So the braking wagon was such way giving its energy to the accelerating one, and at the level of the whole network, that was not harming. That was okay. So this is the advantage of bottom of this approach. And here it's the idea that I think it's genial for the HDL. It's genial, and it should be embraced by the highest possible number of applications in software. This idea, it's just genial. Look, the same circuit can be described in two ways. one way is the behavioral or the functional way. We have here the formula of the function of the logical function. And in the same time, we can describe it in a structural way in which you have the gates. Here you have the actual gates on a silicon that are implementing that function. But the HDL software is working with both of them equally, and the simulations are performing exactly the same if they are well written. So let's say that the customer it's giving you're a producer, an application maker. The customer is giving you a description which is behavioral, functional. He knows what to do, what he needs, and he is describing you what he needs in a very formal and rigorous way with a behavioral description. But then you take this description, and at your company, you are beginning to change it, to turn everything into architectural, to structural implementation. But you can, thanks to the capacity to simulate all the time both approaches, you can use here several teams of programmers that are programming one block or one section of the project. But the project is finished when the description of the application it's 100% structural. But everybody can work, even the teams can work in parallel. That is very effective and very, 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 very nice. Now, about the advantage of the holistic approach, top-down approach, please try to look to this image with eyes, half-closed eyes. I don't know if you will see the final result. I will tell you in the end what it's all about. You see something? Do you see something here or not? I don't know. But the importance of not focusing too close on things, you can miss the big picture. Here it's a picture of Marilyn Monroe. You can see the face, smiling face of Marilyn Monroe. Well, in this disturbing network. So bottom up the traditional way and up down the new way. Now I will finish very fast. I think it's I'm approaching the time limit. How about the parallel shift? The parallel shift is simply replacing the von Neumann computing architectures with full parallel architectures, full parallel. However, in spite of their top performances in terms of speed, cost, energy consumption, FPGA remained for a long time esoteric, rather unknown or avoided by the IT mainstream, ruled by brands like IBM, Microsoft, or Intel. They were reluctant when dealing with full parallel architectures. That was the period, let's say, between 2010 and 8-10 to 2015. Why? FPGA programming is laborious. It's not easy, implying a new and a specific vision, hardware-oriented. On the other hand, dropping decades of achievement dropping the decades of achievements on von Neumann architectures is not easy. It can be painful as a decision for a big company. So that is why even now the applications of PGAs are not very often they are not purely parallel. The people are just emulating with FPGAs other processors. It's coming faster and cheaper, perhaps. I don't know, but this is not full parallelism. Here we have a very still unknown company, but very important European company, which is called Maxeller Technologies, which have a leading role here. Why? Which is the best idea? The leading idea. The parallel shift is often conceived as a massive automate knowledge conversion. Algorithms, procedures from C, for instance, written applications towards HDL. So this is a popular. It's a popular approach because it's effective and it's not producing many obstacles. Although this risks sometimes to miss the full parallel potential. So in that direction, the most companies Xilinx was the first, or all others like Altera, AICTE, Silicon Blue, were new. All of them were new, very fresh, and not very notorious. What was which company was very important to this shift? Parallel shift was Maxeller Technologies, as I told you. The brain behind the Maxeller Technologies is Oscar Manser. Maxeller Technologies originated in London in London, and their product it's famous in this world. It's called Maxeller Accelerator. This Maxeller Accelerator was built only with FPGAs and was designed to turn big projects written, for instance, in C, to turn them into parallel applications. So you see here the cloud. They developed a very powerful cloud only with FPGA computers, which is called Max Cloud. And what is doing these accelerators? It's automatically splitting the big data application programs into thousands or tens of thousands of code kernels, which one process in parallel. Such way, data flows and application loops are accelerating for one or more orders of magnitude. You see, here's the von Neumann, and here it's the accelerator. You take one kernel, 2,000, 10,000. Well, they are not working properly in parallel, full parallel. Why? Because many of those kernels need information produced by the others. But in the end, the result is still they are working in parallel, and the result is much faster than the conventional one. Here it's some images of these computers. And here it's their first application, which was famous. It was about the oil resources in seas. So it was a seismic method. They had a network of tens of thousands of accelerometers that were deployed over the zone, and they were making an explosion, and they were recording the echoes from the bottom of the sea, and out of these images of they were producing an image of the echoes of a whole area and appreciating if there are, it could be oil underneath or not. So you see here, you can see the speed, the difference in speed that was brought by the use of this Maxeller cloud. So in 2010s, companies that were looking for oil had to record all those accelerometers and to send them in laboratories on land. While after that, with the satellites, this process could be done much faster. You see here 100 times faster, perhaps. And here it's the most impressive case. It was a software management application made in 2014 for JP Morgan Chase, which had they were open to the idea to operate faster, though their data covering all the world, you know, and that was the result, which was tested officially in 2015, was amazing. The Maxeller accelerator managed to handle 1,000 times faster the data, the JP Morgan Chase data, than the previous solution. And of course, they wanted, JP Morgan wanted to buy the company, and it was European Commission that stopped this, and they said that this approach is strategic for Europe, and they still sold 20% of the action of the Maxeller stocks to JP Morgan. Now, following this example, the IT establishment begin to consider the parallel shift. And the first to act was Intel with their parallel studio, which was multi-kernel, which was not purely parallel, but still it has a lot of parallel inside. And then many other followed, including, I think here I asked again the artificial intelligence, what are the most important companies that developed parallel computing clouds or services, and you see that is the ranking of GPT. Microsoft Azure was the second after Intel, and most important companies are now playing parallel, are beginning to, and there is a transition now. We are in a stage of transition from Neumann to parallel. So I think I finished in good time, almost good time. Here are the conclusions. I will read them. They are short. While the physical limits of the dominant CMOS technology are approaching, a strategic resource is still accessible, the parallel architectures. A revolutionary shift towards FPGA or ASIC full parallel computing was triggered by Maxeller technologies. The mainstream started to react react after lag, helping IT programmers to meet the parallel shift need for a new vision, hardware-oriented. The new paradigm implies new theoretical studies and a suited university curricula, which is not easy to do. Still, the parallel shift has enough resources to extend the validity of the more than Moore law over the next decades. That is the message, and my final slide. It's about how we should cooperate and not hate us each other. You see, bees are not cooperating very much. One bee, one flower. If two bees are meeting on the same flower, one of them will leave it. The second who comes will look for another. And still, I have here 3 bees on the same poppy flower, and that was because it was a very cold and rainy spring some time ago. And the first day, sunny day, I was out in the garden with the camera, enjoying the sun, and I saw these spectacles of the bees that were hungry and cold and thirsty, and so they were not minding each other. They were working on the same flower to try to survive. And this is our destiny, of course, of humankind. We cannot continue with these stupid wars and confrontations. Here is the confrontation field. Try to make better application, hardware and software and so on. Try to use artificial intelligence in a positive and in a human way. So thank you for your patience, and I finish my presentation, and I'm waiting for your questions or criticism or discussions.
Marius, your talk was excellent, and the way you said that hardware is very humble compared to what software, the tantrums that software gets, in spite of not even contributing to the system as a real, in the real sense. So I think that was a very nice remark to make for that. And also, I hope that kernels in people have heard about kernels in software, and what you demonstrated was kernels in hardware, how they are making the computations very faster. But unfortunately, as you said, if the Moore's law can be exceeded, then what I mentioned in my opening, that Ray Kurzweil would say that if that is the case, then the machines are going to pass the Turing test, and that is going to be the biggest challenge for mankind. We've just seen it in Hollywood, and I hope it doesn't come true. Well, what we saw in 1992 with Arnold Schwarzenegger, we never believed that could be possible. And the Terminator has come back, and I don't think what we are predicting should happen in 2045. Your views?
Well, you see in Ukraine now and in other places, artificial intelligence is beginning to be used in wars. So it's not impossible. It's not impossible, and we must take good care of this, because otherwise, I was until this war, I was skeptical about those ideas. It's dangerous. It's not that. How can be dangerous? Look, it can be dangerous. So we must have a holistic approach and to try to analyze even unexpected facts.
Now, thank you, Marius. We've got another speaker waiting, and there are a few questions which I'll mail it to you, and perhaps you could answer it for us. Let us all thank Marius for his excellent talk. And just to a small thing, that where Marius and Valentina stay is, I think, Marius, am I correct? It's just a 16-hour drive from Ukraine, where the war is waging. Am I correct about that, Marius? They stay just 16 hours away from that. And so, as he said, we have to survive, and we have to work like the bees, as he put in the last picture. Thank you, Marius. Thank you so much. Yeah.
Thank you so much for the attention and for the occasion, for the invitation. It was very, very challenging and very pleasant for me to talk with you.
Thank you so much. We'll keep in touch. Marius, his email
Of
ID
course.
will be shared to you and his presentation. And now, thank you once again. And let's go on to the next session. I think Professor Ranjushri Pal is there online to take over from me. Professor Ranjushri Pal, if you can.
Yes, sir. Yes, sir.
Next speaker, Dr.
Sir, sir. We are waiting for Dr. Sunil, sir.
Yeah. Perhaps you could just introduce. I guess he thought that the talk would continue.
No, I have messaged him, sir. He's joining. Sir, shall I call him, sir?
No, I'll do that.
Yes, yes, yes.
You can start by introducing. Can we just wait for a second before we get Sunil sir online? I think he joined in at 8 o'clock. Yeah.
Sunil sir, I think we can take a 2 minutes break. So till the time Sunil sir joins, so they can come back again.
Yeah.
No,
Let's take
actually,
a
sir, I have already messaged sir to join. I don't know whether he'll be joining soon. So only just maybe 2 minutes, sir, will be allowed. Not much. Because sir is already waiting, right? Sir.
We will just wait for a second to see whether he's joining. In fact, I think he joined at 8.
He joined exactly, and then he left because
the session was going on, and he didn't want to be.
Yes, he told me like that. So now I have messaged him. Shall I call him or what? He has not seen, because he may be already waiting. So now.